Howdy, today in Flippin Science we're looking at the physical properties of organic compounds. So the key ideas in intended student learning is we're going to look at. We're going to look at how the length of the carbon chain affects melting and boiling point. We're going to look at how alcohols of a similar molar mass to an aldehyde or a ketone, how they compare in terms of boiling point. We're going to compare the boiling points of esters to their isomeric acids. Then we're going to be looking at solubility of organic compounds and what affects the solubility. So we're looking at physical properties, specifically melting and boiling points and degree of solubility in water. We're really going to focus mainly on boiling point and solubility. So all three of these factors are affected by how long the carbon chain is and also what functional groups are present in the organic compound. A group like an amine group here, that will increase solubility in a compound because you can make hydrogen bonds between the amine and water molecules. An alcohol group present on a really long carbon chain, however, that's not going to really affect the solubility that much. So that's what we're going to look at today. We're going to look at how carbon chain length and functional groups affect boiling point and solubility. So to start with, we're going to look at the effect of chain length. So we're going to use the same functional group, and all we're doing is we're adding carbons, and we're going to have a look at the effect that has on melting and boiling point. So let's start by having a look at the alcohols. So here we can see we're just adding one carbon on as we go down. So we've got 1, 2, 3, 4 carbons in our chain. And if we have a look at the effect of the boiling point, as we increase the number of carbons in the chain, the boiling point also increases. The effect is clearer on boiling point than it is on melting point, so there's a bit of a mess in the data here. It's all real data. That doesn't mean it's not true, it's just it doesn't really follow the pattern as well as the boiling point does, and that's probably why we're going to focus on boiling point a bit more today. And the reason for this is, as we're increasing the number of carbons, we're going to increase the strength of dispersion forces acting between the molecules. So the longer the carbon chain, the more atoms you have. The more atoms, the higher the molar mass. But really you're adding in more electrons. The more electrons you have, the stronger the temporary dipoles produced when the electrons pull at one end of the molecule or the other end of the molecule and produce a temporary dipole. So the longer the carbon chain, the stronger those dispersion forces, the higher the boiling point. Now we're going to have a look at how alcohols compare to aldehydes and ketones of a similar molar mass. And what happens is you'll see the alcohols will always have a higher boiling point compared to a similar aldehyde or ketone based on the molar mass. And the reason for that is the hydroxyl group that's present in alcohol. So if you look at ethanol down here, we've got the hydroxyl group, the OH group. It's a really polar group. And in fact, it will make hydrogen bonds between other molecules of the same substance here. So the oxygen is quite electronegative, the hydrogen is not very electronegative at all. So the electrons in this bond are hovering around the oxygen. That's almost exposing the proton that's the middle of the hydrogen atom. What that means is this is a very polar group, and that's how we get hydrogen bonding. So the alcohols can hydrogen bond with each other, and that requires a lot more energy to put in to break those molecules apart than if this hydrogen bonding wasn't present. So let's have a look at the aldehydes and ketones now. So aldehydes and ketones do have a polar group. They have the carbonyl group. So there's a delta negative oxygen like we had in the alcohol. But the electronegativity difference between the oxygen and the carbon here isn't as great as the electronegativity difference between the oxygen and the hydrogen. So what that means is this isn't as polar a group, and that means the strength of attraction between these, the dipole that's generated, isn't as strong, which means it's a bit easier to break. You don't have to put in as much energy to break the dipole-dipole bonding between your aldehyde or your ketone. And that has an effect if we have a look at the data. So here we're comparing hexane 1-ol, hexane al, and hexane 2-one. We can see they have a very similar molar mass, but the boiling point of the alcohol is 20 degrees higher, 30 degrees higher, compared to the aldehyde of the ketone. So, although they're all polar, the hydroxyl group in the alcohol is more polar, which means we get stronger secondary interactions, which requires more energy to separate, and therefore a higher boiling point. So let's have a look at some other examples. So here we have propane 1-ol, propanal, propanone. We can see a very similar molar mass, but the boiling point of the alcohol is almost double that of the aldehyde or the ketone. If we have a look, here we're adding a lot more carbons in, so we're up to 10 carbons, so decan 1-ol, decan al, and decan 2-one. Again, the molar mass is similar. The increase in boiling point isn't as significant though, because once we're starting to get this long, the number of carbons in the chain and the dispersion forces acting between the chains is going to have a much greater effect than the simple polarity that's going on with the hydroxyl groups at the end here compared to the aldehyde and ketones carbonyl group. So there's only a 19 degree difference-ish, 20 degree-ish difference between these. So now we're going to compare esters with their isomeric acids. So first we're going to talk about what an isomeric acid is. So we talked about structural isomers before. They have the same chemical formula, so the same number of carbons, hydrogens, and oxygens in this case, but the way they're arranged is different. So same empirical formula if we're going to be technical about it. So if we look at a methyl ethanoate, we've got 1, 2, 3 carbons, we've got 1, 2, 3, 4, 5, 6 hydrogens, and 2 oxygens. If we compare that, we've got another ester that has the same number of carbons, hydrogen, and oxygens as ethyl methanoate. We're taking the extra carbon from here and placing it over here. That has the same number of carbons, hydrogens, and oxygens. But again, we can rearrange that and we can make a carboxylic acid. So this is the isomeric acid of these esters. So that's what an isomeric acid is. So let's have a look at what the effect is. If we compare the isomeric acid to the ester in terms of boiling point, we can see the isomeric acid has a much higher boiling point compared to any of the esters that are isomers of it. So here we can see there's an 80-degree difference between these two. And it's a similar effect all the way through. The isomeric acid has a higher boiling point than the ester that it's an isomer of. And why is that? So the reason for that difference in boiling point is because the carboxylic acid has a polar carbonyl group and also a polar hydroxyl group. So that means that we're going to get hydrogen bonding happening. If we have a look at our little diagram down here, you can get hydrogen bonding between carbonyl groups and hydrogens from a group that can make a hydrogen bond. In this case, it's a hydroxyl group. It's not as strong as a hydrogen bond between another hydroxyl group, for example, down here, but it's still reasonably strong. And again, when we're talking about strength of bonds, we're talking about the amount of energy required to separate these molecules. So the isomeric acid will form hydrogen bonds between the acids, and that requires a lot more energy to break than the secondary interactions that are occurring between the esters. The ester does have a polar group, so it's got this polar carbonyl group here, and there's also a polarity difference between the carbon and oxygen down here. But the strength of the dipole generated by these polar groups here isn't anywhere near as strong as the hydrogen bonding that's generated over here. So hydrogen bonding requires a lot more energy to separate than a similar molar mass, the dipole generated in the ester. So that's why the isomeric acid will have a higher boiling point. Now we're going to talk about solubility. And solubility in water depends on a few things. It's the functional groups that you have present and whether they can make a secondary interaction with water, and also how long the carbon chain is. So a polar group, like in alcohols, here I've got diols, dicarboxylic acids, and diamines. So if you have a functional group that is polar and can make a secondary bond with water, specifically it would be great if it could make a hydrogen bond, and it's small, it will be soluble. But if we have a look down here, our classic example here is oil and water, and they just don't mix. And the reason for that is, well, we'll have a look in a minute and we'll see why that is. So to be soluble in water, you need to be reasonably small, and you also need to make some kind of secondary interaction with water. So let's have a look at an example in terms of solubility for a homologous series. In this case, it's aldehydes. So let's have a look at how soluble they are in water and what happens when we add carbons. So as we go down here, we're adding carbons. So 1, 2, 3, 4, 5, and then we've got 8. So we're making a bit of a gap down here. Methanol is completely soluble in water. You can put as much methanol in water as you like, and it will completely dissolve. Then as we add an extra carbon, we're reducing our solubility from basically miscibility, to only 16 grams per 100 grams of water. And then if we add another carbon, we're halving that again. As we're adding more and more carbons, we're adding less and less soluble until at 8 carbons, the aldehydes are just not soluble anymore. So once we have, say, 8, 9, 10 carbons, they just won't dissolve in water, and you'll get that extra layer forming, like we saw with the oil and water before. And this is the pattern that you'll see in your organic compounds. If you have a polar group, so an aldehyde does have a polar group, but as you add carbons, you're reducing its solubility. So the longer the carbon chain, the less soluble it is. So all this comes down to water. Water is a very small molecule, and it also can hydrogen bond with itself. So different water molecules can hydrogen bond with each other. So to be soluble, you need to be small enough to sit in between those water molecules, but also make some kind of secondary interaction with those water molecules. And if you can't do that, you won't be soluble in water. So here we have an alcohol. This is ethanol. So we've got a very polar hydroxyl group that can make hydrogen bonds with water molecules. So it's small. It has a functional group that can make a secondary interaction with water. In this case, it's a very strong secondary interaction. It's a hydrogen bond, so that will make it very soluble in water. Over here we have a triglyceride. So this is like an oil or a fat, like we had in that picture before. We had oil not mixing with the water. It has this several really long non-polar carbon chains. It does have a bit of polarity at the top, but the polarity at the top doesn't overcome the lack of polarity in the carbon chains present here. water molecules won't be able to make much of a secondary interaction with these nonpolar carbon chains. So because of that, it just doesn't dissolve with water. It can't sit between the water molecules, and it's not making a secondary bond with water molecules. So when you're looking for solubility, you're going to be comparing normally one compound with another. You're looking at length of carbon chain and the number of functional groups that can make a secondary interaction with water. So that's what you're going to look for. So here's an old exam question. So here we have amphetamine. Amphetamine has low solubility in water and is usually taken in the form of salt. Using the structural formula above, explain why amphetamine has a low solubility. Now, the key is it's low solubility, not insoluble. And the other key is this is for 2 marks, so we need to have 2 ideas that we're talking about here. If we have a look at the structure for the amphetamine, we can see there is an amino group here, an NH2 group, an amine group. What that means is this is quite polar. Nitrogen, hydrogen, oxygen, hydrogen, fluorine, any of those bonds, they can make hydrogen bonds with water. So this group will be able to make hydrogen bonds with water, and that will lead to some level of solubility. But we have a really long carbon chain here. Here we have a benzene ring. So this aspect of it won't be particularly soluble in water, particularly the benzene ring. They're not very soluble in water at all. So the reason why it has a low solubility, it does have some aspect of solubility due to the amino group here that can form hydrogen bonds with water, but the presence of a long carbon chain will reduce its ability to dissolve in water to a level where it would be mostly insoluble, I would suggest. So today on Flipping Science, we looked at the physical properties of organic compounds. That's it for Flipping Science today. See ya.